Okay, so one more topic from chapter 3. Differentials. So let's take a look at sort of a general curve. A piece of a curve here. So exactly what that function should be, and your curve can look a little different. And I'm going to go to a point on that curve. And the x value there, I am going to call x sub 0, x naught. And of course, the height of the curve at that point, since you always get the y values by plugging in the x value, that's just going to be f of x naught. Now I'm going to move over by a small distance. And I'm going to give that distance two names. I'm going to call it delta x. And I'm also going to call it dx. Like dx, like as in when we write dy dx, when we use Leibniz's notation for derivative. So it has two names, delta x and dx. And both of these things are the distance that I start at x naught and move over on the x-axis. And so if I start here and move over, then this point right here is either, we can call it x naught plus delta x or x naught plus dx. It's the same thing. That's that x value. I don't know if this symbol, this little triangle symbol for delta, is new to anybody. It's a Greek letter, the fourth Greek letter of the alphabet. And if you've taken a physics course before, sometimes in other sciences, they use delta to mean change in it. So delta x, the change in x between here and here. Now let's go up to the curve. Vertical line, what we'll be able to do. Now, on my curve, that looks like it's right up at the top of the hill, but that's sort of incidental. It doesn't have to be at the top of the hill. It just happens to be where I drew it. And I'm going to keep this vertical line going a little bit. Now, at my original point x naught, I am going to draw a tangent line, the line which just grazes the curve there. Now, you can see that the tangent line, obviously its height doesn't equal the height of the curve at x naught plus delta x naught, but if we're not too far away, they're close. That's almost what makes a tangent line a tangent line. It's the line which hangs around the curve best of all possible lines that touch the curve at x naught. That's basically what a tangent line is. It stays as close to the curve for as long as possible of any line right around x equals x naught. Now, between x naught and x naught plus delta x, or x naught plus dx, the curve climbs by by that much. The curve goes from this height to this height. We're going to call that delta y. That's how much the curve changes between x naught and x naught plus delta x, or x naught plus dx. Now the line doesn't change exactly that much. The line changes more on my picture. So the distance between here and here, the amount the curve grows is delta y. The amount the line grows is dy. We're going to call that dy. So delta y and dy are not the same, unlike delta x and dx, which are exactly the same. This dx and the dy are called differentials. Dx and dy are called differentials. Yep, dx is exactly equal to delta x. That's how we defined it. Dy is not exactly equal to delta y, but if delta x is small, then dy is approximately, hard time writing so low on the board, is approximately equal to delta y. They're close. These two are exactly the same. If delta x is relatively small, then dy and delta y are relatively close. In other words, sort of in basic English, if dx or delta x is small, if the amount we move over on the curve is relatively small, the change in y value of the line, of the curve, I should say, is approximated by the change in y value of the line. That all seems kind of intuitively obvious and relatively straightforward. That's right. There's nothing terribly deep going on here right now, other than the fact that there's sort of a lot going on in this picture. Okay, so the practical upshot of this is that for values near x naught, we can use the line to approximate the values of the curve. Hence, we can use the y values of the line to approximate the y values of the curve. This is called linear approximation. Near x equals x naught. We can use the y values of the line to approximate the y values of the curve near x equals x naught. The further away you get from x equals x naught, the further the line and the curve diverge. They get further and further apart.
Is that an equal sign? Like it says
Right here?
no underneath the graph. Yeah, that right there.
Yeah, this is an equal sign. So
Okay.
since delta x and dx are exactly the same, then writing x naught plus delta x and x naught plus dx, it's exactly the same. It just depends on what you want to emphasize. On the whole, though, how's this new camera working? Is the picture on the board clearer?
It looks a lot better. Yeah.
Okay, good, good. I'm glad to hear that because it's hard enough studying remotely, with under the best possible conditions. I certainly don't want to make it harder by having, a fuzzy picture. Okay, so in that case, if delta x is small, so taking what we've written in words and putting it back into symbols, f of x naught plus delta x, the y value at this new height, the y value at that dot right there, is approximately equal to f of x naught, the y value at this original point, plus the distance that we moved over, which is delta x, times the slope of this line. But the slope of that line, one more thing on this picture, is just f prime of x naught. So what I just wrote is the height of that dot is pretty close to the height of that dot. That's all that says. Let's put this into action. I think I'm going to leave that picture there for now. Use linear approximation. To estimate the value of the square root of 101. Use linear approximation to estimate the value of the square root of 101. Okay, the first thing we need is an x naught. The x naught, oh, sorry, take that back. Before we even get that far, the first thing we need is a function. The function in this case is going to be the square root of x. So, step one, write function. Since we're trying to compute the square root of something, f of x is going to be the square root of x. Step two, is going to be find x naught. So write x naught. And that's a nearby value to 101 that is easy to compute the square root of. So You give me a value somewhere in the vicinity of 101 that it's easy to take the square root of?
100.
Yeah, 100. Perfect. In fact, when you're looking at this, square root of 101, it's clear that the answer is going to be a little bit bigger than 10 because the square root of 100 is 10. And 101 is a little bit bigger than 100. So that should be obvious to somebody who's never even come into a calculus course. So step 3, write delta x. You can see I'm doing more writing step 1, step 2, and step 3 and explaining what those are. So delta x is going to be the distance from x naught to the point that you care about. This is the x value you want to compute. How far is it from 100 to 101? I don't mean to insult your intelligence, but just somebody say it.
1.
1, right. So delta x is 1. And I hardly even, want, let's go ahead and write the derivative. Because we're going to need the derivative. We'll call that step 4. So if f of x equals the square root of x, in other words, x to the 1/2, then f prime of x equals the 1/2 comes down, x to the 1/2 minus 1 is minus 1/2. And writing something to the minus 1/2 is the same thing as writing 1 over x to the 1/2. So 1 over x to the 1/2. And of course, x to the 1/2 is the square root of x. So this is 1/2 times 1 over the square root of x. In other words, 1 over 2 root x. Okay, so step 5, plug everything into the formula. And by the formula, I mean the thing in the box. So the square root of 101, in other words, f of 101, since f of x is the square root of x, is the same thing as f of 100 plus 1. I mean, 100 plus 1 is 101. I haven't done anything yet except use arithmetic. So according to the formula, that's approximately equal to f of 100, in other words, the square root of 100, plus delta x, which is 1, times f prime of 100. So f prime of x is 1 over 2 root x. So f prime of 100 is 1 over 2 root 100. I mean, we could pull out a calculator at this point, but I don't think we really need to. So this is equal to root of 100, of course, is 10 plus 1 times 1 over 2 times 10. So 10 plus 1 over 20. again, I don't really think we're going to need a calculator at this point. If 1/10 is 0.1, then this is telling you it's half of that, or 0.05. So this is 10 plus 0.05. In other words, 10.05. So this isn't really how high the square root curve is at 101. It's really how high the tangent line to the square root curve at 10 is at 100 is at 101. So this is an approximation. It's an approximation. It's not the real value. But it was easy to compute because working with lines is much easier than working with curves generally. Working with lines is much easier than working with curves. So right now, the application of linear approximation that we're looking at is a lot like what we were doing Newton's method. It has to do with efficiency. So doing things efficiently. We're trading a little bit of accuracy, a lot of ease, at least a lot easier than it is to take square roots in this case. Somebody pull out a calculator now. You can use the calculator app on your phone if you like. And give me the real value that, well, it's only going to give you the value to whatever it is, like 9 or 10 places. Give me the first 4 or 5 places, or when you take the square root of 101. So the real value is 10.0.
It's 0.04987.
Excellent. So you can see how close these two numbers are. They're very close. They're closer than 1/1000. You know, 0.049 is only 1/1000th away from 0.050. And so this goes on. So for a small trade in accuracy, we got a whole lot of ease. This was a computation to do. Just out of curiosity on my part, did anybody learn how to take square roots of things that didn't work out evenly in school using pencil and paper? Just curious. They don't teach it much anymore. In fact, they discontinued it before I even got to high school. There's a method, believe it or not. If you want to look it up, it's called the double down method of taking square roots. It looks a little like long division, but there is a way.
I think I did, but I don't really remember.
You learned that? Okay, cool. It's pretty rare now. As I said, it was discontinued in my school system before I got to high school. The only way I learned it as a kid is one of my babysitters taught me when I was a little kid. So that was pretty cool. So yeah, so there is a way of doing it. It's a lot more work than what we just did right here. So we just used the linear approximation method based on the differential stuff. Now differentials are going to come back in the next chapter, and we'll be using them a lot. So, you know, when we write dy dx to mean like y prime, Newton's notation, Leibniz's notation, I told you right away that this thing isn't a fraction, but we're going to start treating it as if it were a fraction. And we'll get back to that next chapter. I just want you to know that the top and the bottom, we're going to start breaking those up, and we're going to treat them as if they really are a fraction. We're going to treat them separately, and the top and the bottom independently. Those things are called differentials. But right now, the only part of differentials that I want you to understand is that we used the straight line to approximate the curve around the point where they were tangent. So how do you feel about this tangent line approximation business? Is that okay? Okay, 2 thumbs up. Okay, I would assume it's okay. If there are any questions, feel free to ask. But that's it for chapter, cool. That's it for chapter 3. We are basically on to chapter 4 now. We're coming into the home stretch of the course, believe it or not. So let's see, I'll leave that up temporarily. section 4.1 is called antiderivatives. Antiderivatives in indefinite integration. I'm just going to say antiderivatives for now. Let me just put up the answer to a question, and then I'm going to ask you what the question was. So say the derivative of some function is 2x. What was the original function? What function did somebody take the derivative of?
X squared.
Yeah, x squared. So if I take the derivative of x squared, I get 2x. Is that the only possible function that somebody could have taken the derivative of to get 2x? Here's a hint. No. Give me another one.
1/2 x squared.
Well, 1/2 x squared. If I took the derivative of 1/2 x squared.
Oh, yeah, that's not right.
Yeah, but that was a great suggestion. The 2 would come down, multiply the 1/2, and just give you 1, and you'd end up with just plain old x. So that's sort of on the right track, but we put you picked a constant, you just put it in the wrong spot. So it is going to be a variation on x squared, but the constant doesn't go in front of the x squared. So there are other possibilities. X squared. What are we going to do with a constant besides multiply?
Divide or subtracting.
Yeah, add or subtract it. So I can take x squared plus, I don't know, 5. If I take the derivative of x squared plus 5, the derivative of x squared is 2x. The derivative of 5 is 0. So it still works this way. Or f of x equals x squared minus 30. Derivative is still 2x. It doesn't matter what I add or subtract. I'm still going to get 2x there because the derivative of anything I add or subtract is 0. So in general, the original function could be x squared plus any number. I don't have to write plus or minus any number because c could be negative. In this case, c is negative 30. If I add negative 30, it's the same as subtracting 30. So f prime of x equals 2x is the derivative of x equals x squared plus any number. And turning that around, f of x equals x squared plus c is the antiderivative of 2x. So I don't know if you've ever watched a show, called Jeopardy. It's a game show, but the gimmick there is they give you the answer and they ask you what the question was. It's the same thing here. We have a notation. We use this notation, an elongated S, and then you put your function inside. And then this should look familiar after that last section, a differential. This just says what is the antiderivative of 2x? And you already told me that it's x squared plus or minus any number. So this symbol, which we call an integration symbol or integration sign, and this dx, think of them as open quotes and close quotes right now. Just think of them as open and closed, and whatever's inside, you're taking the antiderivative of. So think of this is all part of one symbol. Just like open quotes and close quotes. Those don't really do anything by themselves. You put something in the middle and they function together as part of one symbol. So open quotes, the thing you want to take the antiderivative of, close quotes. So the antiderivative of 2x is x squared plus c. So let's do some antiderivative problems. So we've done our first one already. The antiderivative of 2x is x squared plus c. How about the antiderivative of x, since you brought it up earlier? If the antiderivative of 2x is x squared plus a constant, what's the antiderivative of x? What do you take the derivative of to get x? Somebody already mentioned it, really. Since x is half as big as 2x, what do we replace the x squared by?
1/2 x squared.
Yeah, 1/2 x squared. And it's always easy to check your answer because we can just go ahead and take the derivative of this. If we take the derivative of 1/2 x squared plus a constant, the 2 comes down, multiplies the 1/2, they go away. X to the 2 minus 1 is x to the 1, and the c goes away. That's perfect. That's just right. How about this? The antiderivative of 3x squared. What did somebody take the derivative of to get 3x squared?
X cubed.
X cubed, right. We're going to put in our plus c. We always write the plus c when we're doing antiderivatives. But yeah, oops, sorry, x cubed. X cubed, right. Yeah, if you take the derivative of x cubed, the 3 comes down, you write your x, the 3 becomes a 2. And of course, the c goes away. So checking an antiderivative is always easy. Finding an antiderivative is harder than finding a derivative for the same reason that walking backwards is harder than walking forwards. You can't see where you're going. How about this? What's the antiderivative of plain old x squared? If you could go from this question to this question by noting that when we went from 2x to 1x, the thing we wanted to take the antiderivative of was half as big. So we put a 1/2 here. You can go from this one to this one, noting that what we have here is only 1/3 as big as what we had there.
Would it be like 1/3 x cubed?
Absolutely. And again, you can always check your answer. If we take the derivative of 1/3 x cubed, the 3 comes down, multiplies the 1/3, they cancel. You write your x, the 3 becomes a 2, and there it is. And the c goes away, of course, as always. Yeah, you're doing great. Okay, let's do another one. How about the antiderivative of 5? Not the derivative of 5. Derivative of 5 is 0, of course, because it's constant. But what could you take the derivative of to get 5?
5x.
Excellent. Write our plus c. Before we go on, is this making sense? Is this working for you so far, other than the fact that it feels really unnatural because it's backwards? Cool. How about this? The antiderivative of cosine of x. What did somebody take the derivative of to get cosine?
Negative sine x.
Ah, careful.
Just sine x.
Yeah, just plain old sine x. Derivative of sine is cosine. So the antiderivative of cosine is going to be positive sine, but you're correct that the derivative of cosine would be negative sine. So based on past experience, I can tell you that now that we've introduced antiderivative and the signs are different, it's going to mess you up for a few days. But it will all straighten out in your head if you do enough of these. How about this? What did somebody take the derivative of to get e to the x?
It's just e to the x.
Sure is. We'll put in our plus c. Let's make it a little bit harder. How about this? Maybe this isn't any harder. I don't know. Do you remember what you take the derivative of to get 1 over x?
Log x.
Excellent.
Log x.
Yeah, log x, right. ln of x. I wasn't sure if you'd remember that because we haven't used it for a while. And how about this? Let's put some of this stuff together. How about x squared plus x plus 5. You already know the derivative, the antiderivative of x squared, and you've already seen the antiderivative of x, and you've already seen the antiderivative of 5. So I think you got a pretty good shot at this.
1/3 x cubed plus
X cubed.
plus 1/2 x squared
1/2 x squared
plus c
plus 5x
plus
c. Yeah, and you can, and if you're just guessing, you can always double check to make sure it's right. Take the derivative of 1/3 x cubed, the 3 comes down, multiplies the third, they cancel. You have x to the 3 minus 1 to the 2. So the derivative of 1/3 x cubed is x squared. Derivative of 1/2 x squared is x. Derivative of 5x is 5. Derivative of c goes away. So I admit, we are walking backwards right now, and this probably feels very, very unnatural at first, just because it's not natural to walk backwards. You can't see where you're going. But the idea behind it, I'm hoping, is increasingly clear in your mind. And I think you put in a good day of work, and we're just going to end a little early today unless you have any questions. In that case, have a good one. I will see you all on Wednesday.
I have a
Thank
question.
you.
Oh, yeah. Sorry, who?
It's not really pertaining to this lesson, but for the finals, is it gonna be like everything that we've learned for the year, or is it just gonna be like from the last midterm?
No, it's cumulative.
Okay, and then would it be open notebook or closed?
It's closed.
Okay, and it's gonna be similar to the questions that you give us on the midterm.
If you have done the midterms and you're feeling comfortable with the midterms, then you should feel very comfortable with the final exam. Some of the questions, other than the fact that like I changed the numbers or changed the problems, will be almost cribbed off the midterms. But I basically just put everything together, hit the highlights of the course. I'm not trying to scour the four corners of the course to find the most obscure stuff that I possibly can. I'm honestly not here trying to mess you up. I'm trying to make it as easy as possible for you. And so it should be familiar material. Now, if you take a look at the schedule, for a long time we were behind our schedule, but we've actually gotten ahead of our schedule now, which is good, which means that we should have time during the last week of class, not the whole last week, but part of the last week, to do review. And so I'm hoping by the time we hit the final exam, everybody will feel very comfortable and you'll have lots of chances to ask me questions about things that still aren't clear to you. And we can remind ourselves of things that you understood, a while ago, but have forgotten. But it will be cumulative, everything from basically after the review test till the end of the course.
Okay, thank you.
Of course, my pleasure. Any other questions? Okay, I will see you all on Wednesday.
Thank you. Have a good day.
You too.